Okay, so this chapter is about electromagnetic oscillation and alternating current. So actually, chapter 27 and chapter 31 is a summary of a circuit analysis, which will be a one semester course content. So there will be lots of content, especially in this chapter. So let's begin. So first of all, we'll talk about the LC oscillation, and then followed by damped oscillation in RLC circuit. Next, forced oscillation of free simple circuit. Then we'll talk about the series RLC circuit. In between, we will talk about the phases for the RLC. And actually, some of the notation in the textbook is not, in my opinion, not so good. So actually, I have rewritten some of the formula in this chapter, especially in the about the phasor. So please pay attention to that. So next, we'll talk about the power in alternating current AC circuits, and finally, briefly talk about the transformer. So for the electromagnetic oscillation, well, it looks lots of content, but basically there are eight process. Without loss of generality, we can start at this case. So for all these figures, for all these small figures, actually there are an inductor and a capacitor in series. So for this one, some energy is stored in the capacitor. Some of the energy is stored in the capacitor. So, so you can consider it something like a simple harmonic motion. There is some energy which is kinetic energy and the potential energy. And actually, without any loss, then the energy should be conserved. In this case, the energy for kinetic energy can be converted to potential energy and vice versa. And actually, this is similar. So for this case, the energy is stored at the capacitor in the electric field, and then in this case there is no current. And then the current will be going to the left side, and some of the current in the E field will convert to the energy in the B field, so that half of the, so at a specific moment, half of the energy will be stored in the electric field and half of the energy will be stored in the magnetic field. And then move forward, and then until all the energy is converted to the energy stored in the magnetic field, and then at this moment the current is maximized, and then the current will decrease, and until a specific moment half of the energy turn back into the energy stored in the capacitor, and then all the energy and they go back to this state, but for this case, the top plate is positive, the bottom plate is negative, but for this case, the top plate of the capacitor is negative, the bottom plate of the capacitor is positive. So this is not the same, but in terms of energy, they are the same, because the energy stored in the capacitor is 1/2 CV square. So no matter it's V square or negative V square, then it is still V squared. So in this case, the energy is the same, but the polarity are different. So it keep moving on until it will go back to this state. It was something like a simple harmonic motion, just like something that you have a string. Maybe you connect a ball, so there will be the least kinetic, maybe not so good in this way. Maybe we should start from this case. So at the beginning, all the energy are potential energy, and then you release the ball, and then it will go to it will go to here, so that all the kinetic energy is converted to all the potential energy will be converted to kinetic energy, and then it would further move forward to this position, and then all the kinetic energy convert back to the potential energy. But in this case, they have the same level of potential, but actually the position are different, just like this case and this case. And then this mass will go back, and go back to this, and then we will loop forever without any loss. So actually, as we have learned in chapter 25 and chapter 20, maybe chapter 30, so we know that the energy stored in a capacitor and the inductor is something like this. UE is Q squared over 2C, or 1/2 CV squared, or whatever. UB will be 1/2 Li squared. So actually, the top one is also equal to 1/2 CV squared. But for the bottom case, it is proportional to the square of the current. So, and actually, the energy should be conserved. So in the textbook, it also compared with the block spring system or the spring mass system. So actually, for the spring mass system, spring has a potential energy 1/2 kx squared. And the block has the mass has the kinetic energy 1/2 mv squared, where v is the velocity, velocity, which is the first derivative of the displacement. And likewise, for the LC oscillator, the energy for the spring is the capacitor, so that the electrical energy stored in the E field, which is 1/2 Q squared over C. So you can regard X is Q and K is 1 over C. And the energy for the block or the mass is the inductor. So the inductor stored in the magnetic field is 1/2 Li squared. So that you can regard V is the I in this case, and actually X, the derivative of X is V, so that we have V here, and then the derivative of charge is the current, so that we have Q here and I here, and then L is energy to to the mass, something like this, so that we can make the analogy between the spin mass system and the LC oscillator. And actually the natural frequency of the LC circuit is nothing but omega equals to 1 over square root of LC, or if you use the frequency, it will be 1 over 2 pi square root LC. So this is the omega is the angular frequency, F is the frequency, the frequency. So in this case, in the textbook, it will use two methods to demonstrate the cases. So one is the energy method. Actually, I think it has used it in the previous chapter also. And what I really used to is the potential method. No, I think in the textbook it only presents the energy method but not the potential method. But actually I used to the potential method, so I also tell you about the how to use the potential method to get the same results. Actually, energy method I have not actually I have not seen the energy method before. I have read several circuit textbooks which will not use the energy method. It is some kinds of physics point of view, very physics stuff. And actually I think it is quite interesting, but I'm not used to using that, but it's worth to take a look. So for the energy method, it considers the total energy is U total energy for the system, for the LC oscillator. So present at any instant in the LC oscillator or the oscillating LC circuit is given by this, which is the energy stored in the magnetic field and also energy stored in the E field. So it is nothing but 1/2 Li squared plus Q squared over 2C. So this is the total energy, and we assume in this case there are no losses, no energy losses. So the energy should be conserved. Okay, so you can see here the conservation of energy, and as long as there are no resistance in this circuit, so no energy will be transferred to thermal energies, which means there are no energy loss, and U should remain a constant with time. Or equivalently, we can write it as du dt equals 0. du dt equals 0. So we have the expression of U. So we can take the derivative of this expression. So for this one, L suppose is a constant to time. So L, you can just pick it out. And then I is a function. So I squared, we take the derivative is 2I, but don't forget the chain rule, so we need to multiply it by di dt, which is, this term is due to the chain rule. And for the second term, C is also a constant to time, so C is just, you can just pick it out, and then we take the derivative of Q squared, which will be 2Q, so 2 and 2 cancel. And also we need to use the chain rule, so we still need to multiply dq dt. Okay, so as long as du dt is equal to 0, so this one is equal to 0, this one is equal to 0. However, I is the first derivative of the charge with respect to time, so we can also write it as di dt equals to the second derivative of the Q. So with this substitution, we can write actually this didt substitute into here. So we have a second derivative of the charge, and actually dq dt, yeah. So actually, Q is dq dt is actually I. So actually, they will not be. This will not be a function equals to 0. So I and dq dt, I and dq dt can be cancelled, and this one is dq d2q dt2. So this one is this one, and we have q over c, and then we all multiply by L multiply by L, so that we have LC here, so that we have this expression, which is a second order ODE. As long as we have no EMF or voltage source, so on the right side there is only a 0. It's only a 0. Likewise, we can use the potential method to really get the same. Sorry, this is not capacitor. So here in this case, this is inductor, this is capacitor, and we assume this point is a ground node, and this is L, this is C, and thus this is this is V, this is V. This is positive, this is negative, and in this case, for the inductor, V, this is negative, this is positive, because according to the KVL, the voltage going for this loop should be 0. So this is V. So this is this would be minus V. This would be minus V. So this is V. This is minus V. And actually, this is I. This is I. This is I. They share the same. They share the same current. So in this case, we know that I is C dV dt. C dV dt. And for the inductor, we have minus V equals to L di dt. Because I is going upward, so we need to consider the voltage, or the voltage difference, minus V, which is this side is positive, this is negative, to match this current. So we get that we get minus V equals to L di dt. And in this case, this I and this I is the same, so we can just substitute L. We can just substitute C dV dt into this equation. So next, we have LC times the second derivative of V, something like this. So we divide LC on both sides, so that we will have second derivative of the voltage equals to 1 over LC V equals to 0. But you feel like this is not exactly the same as this one. In this case, the variable is Q, but what I derive is actually V. But actually, as long as we have a linear circuit, RLC are all linear components, so actually we can still get second derivative of I equals to plus 1 over LCI, which means that I also satisfy this equation. Also, the second derivative, also Q also satisfying this equation. The reason is simple, which is something like, so first maybe we can consider this one first. As long as we derive this one, then we can actually take one more derivative of that equation. So that it will become d dt and then dv dt, something like this. And also for that one, dv dt, something like this. You take one more derivative, which is fine. So we can take one time and then take the other 2 times. And then we can multiply the equation by C. As long as C is a constant, so that we can just put it inside. So in this case, this is I, because we have this expression. So that I also satisfying this one, and as long as we know that I equals to dq dt, which means that as long as if we substitute this one, we only need to consider that we take one more derivative to this equation, and then it will become this one. So actually, because they have only linear relationship between them, so that all the variables should satisfy this equation. So when we consider the spring mass system like this, we have a spring connecting to a mass, and as long as we consider this is the original position, which is x equals to 0, and the x-axis is something like this, and this mass is m. The spring constant is k. Which means that according to Hooke's law, F is nothing but minus kx according to the Hooke's law. So F equals to kx, which is the Hooke's law, and according to the Newton's second law of motion, we know that it is ma, and a is actually the second derivative of the displacement, something like this. So as long as we move it to the right side, so we have a m d2x dt2 plus kx equals to 0. So we divide m for this equation. So we have a second derivative of the displacement plus k over mx is 0. So as long as we try to solve this second order constant coefficient of d, so we will write like this. Second derivative, we change it into s squared, and then the original function, we change it to 1, so we have s squared plus k over m equals to 0, so that the root will be plus or minus j square root of k over m. Square root of k over m. Yeah. And actually we'll call omega is k over m. We can define this is the natural frequency of the spring mass system. So it can be written as plus or minus j omega, or omega 0 is just. So in this case, as long as we have these two roots for the characteristic equation, or so the expression for x will be a cosine omega t plus b sine omega t. It depends on the initial condition, which is because it is a second order ODE, so it depends on x0 or x t0, and also the first derivative. The first derivative of at 0, or we can write it as dx0 dt. Usually we'll use a dot for derivative with respect to time. X prime will be the derivative with respect to the space. Maybe x, y, we will use x, we'll use prime, but for time we'll draw a dot at the top of the variable. So actually, but usually in the textbook we will not use this expression. Actually, they will write it as something like r cosine omega t plus or minus phi. It depends. Plus or minus is not a great issue. It's not a great issue, but when you learn the trigonometry function in high school, you should know that the cosine and sine function with the same frequency can be written as a single one. So this is the magnitude. So r will be square root of a squared plus b squared, and this is the phi, and actually tangent phi will be I'm not sure, minus b over a, minus b over a, something like this, because we have a cosine. This cosine should be equal to cosine omega t cosine phi minus sine omega t sine phi. So we can write it like this. And usually we can, for some cases, we can assume that the phi is 0 to make this expression even look more clean. So in this case, the textbooks tell you that the charge for the for the LC circuit is nothing but big Q is a constant, and then multiply by a cosine function, something like this. And actually, the current will be just a first derivative of the charge, which is something like this. Because you take the derivative, you use the chain rule, so you multiply omega, and then cosine will be minus sine, So the current is something like this. Okay. So next, we consider the electrical energy, which is Q squared over 2C. So in the previous page, we have the expression for Q, small q, so that we substitute it here. Then the energy stored in the electric field will be like this. And also, we know that I has an expression like this. So the energy stored in the magnetic field is 1/2 Li square. So it will be something like this. And also it used the relationship of the omega is equals to 1 over square root of LC, so that it can also express as like this. Otherwise, you will have a term omega square. So omega square will be 1 over LC. So the L will be cancelled. So the expression can be something like this. And this is very interesting because when we add them together, cosine square plus sine square, this argument is the same. So cosine square plus sine square is 1, so that when you add them together, it will be Q square over 2C. So it tells you that the maximum value of QE, QB are both Q square over 2C, because this is when this term cosine and sine square, the maximum value of cosine square and sine square is 1, because cosine and sine are the function between -1 and 1. So when they have a square, then the maximum value is 1. So it will be between 0 and 1, something like this. And as long as you know as you have learned the trigonometry function, you know that cosine square x is 1 plus cosine 2x over 2, and sine square x is 1 minus cosine 2x over 2, something like this. So it still looks like a sine function, but only shifting up. So the maximum value is Q square over 2C for both QE and QB. And at any instant, the sum of them are equal to Q square over 2C, because you know that cosine square plus sine square is 1, nothing but 1. And when Q is maximum, UB is 0, and vice versa. So here's a sample example. So a 1.5 microfarad capacitor is charged to 57 volts. The charging battery is then disconnected. A 12 millihenry coil is connected in series with a capacitor, so that LC oscillation occurred. What is the potential difference? VL across the inductor as a function of time. As a function of time. So in this case, so as we know that the second derivative of Q plus 1 over LC Q equals to 0. Something like this. Q would be capital Q cosine omega t. Cosine omega t. Omega is 1 over square root of LC. In this case, we should calculate that Q will be CV. Q is CV. So C is 1.5 times 10 to minus 6, and V is 57 volts. So Q is 8.55 times 10 to minus 5 coulomb. Then we should know that VL is L di dt, L di dt, which is L second derivative of Q with respect to time. Something like this. So we can just substitute. We can substitute this one into here. So in this case, we will have second derivative, so that we will get omega square, L omega square Q, and then we have minus I, L omega square Q, and then cosine omega t. Because cosine omega t, we take the first derivative, which will be minus I omega t, and then we take one more derivative, which will become minus cosine omega t. So we have a minus I in the front. And then omega is nothing but 1 over LC. So that L and L can be cancelled. We have omega square Q over C. Q square, no. Omega square already turned into that term. So it will be minus Q over C cosine omega t. And actually, Q over C is nothing but V. So we have minus V cosine omega t. So we know that omega is 1 over square root LC. So it will become 12 times 10 to minus 3, and C is 1.5 times 10 to minus 6, and then we take the square root, which will become 7.5 thousand, which is radian per second. So you should care about the unit. For angular frequency, the SI unit is radian per second. For frequency, the SI unit is hertz. So in this case, it is minus 57 cosine 7500 T in volts, something like this. So this is part A. So for part B, what is the maximum rate of dIdt at reach the current change in the circuit? So actually, we know that I equals to minus omega Q sine omega t, not cosine. Sine omega t. We have the expression here, here. So that's we have di dt, which will be minus omega square q cosine omega t. And in this case, di dt max is nothing but omega square q, because when this one is -1, then it would be the maximum value, because cosine is between -1 and 1. So in this case, omega square is 1 over LC, so it is Q over LC, Q over LC. And Q over C is nothing but V, or Q equals CV, and cancel the C. So we have V over L, V over L. So the answer, we substitute the number. The V is 57 volts, L is 12 millihenry, something like this. So the answer will be 4,800 A over S. A over S. So when we consider the unit for this term, we have I. So we have ampere here, and then time, so that we have second. So which is, so the Leibniz notation is good when we consider the unit. So just like you divide the current by the time. So for the SI unit is same as the ampere over second. Okay. So